I'm not trying to say you have to use this specific design, but when I was looking at the schematic, I think that could be a really doable way to design that amplifier. I just call it BOOM, okay? Bill of materials. So probably you can learn a little bit from the way that I search for parts. So I was looking at multiple solutions. I think the first one has this schematic because this was built probably in either KiCad or Altium, and it looks pretty nice. And there's a video demonstration, so I choose to trust it. Okay, even though I do have another schematic that I used for my analog circuit design a few years ago. It's about 2020, I think. But I want to try something new. It's always the case. Don't want to use the old things that I know. I know it's going to work, right? And the thing is, instrumentation amplifier is very expensive. Every single one is like $20. I want to try something different. So let's see. First, we need, if we do all the caps, let me zoom in. Do the caps. And what this guy used here, if you look at the schematic, so it's not showing the circuit board about the footprint of the parts. Let's just choose whatever we can find out. Okay, so caps 100 picofarads and resistor 1 megafarad, 1 mega ohms. So we have it. This is something we have in the lab. Let's just mark this one, right? We have it. And I believe we have this as well. It's a ceramic material. Let's say footprint. It's a ceramic. And this is just a rod. Okay, sometimes it's called axle, I believe. It's just a regular resistor to be built on the, we're not making a PCB, okay? And this part, I feel that we can use the one that I used for the car, for the little car. It's the IR line tracker. Let's see, put a quantity here at another column. Quantity. This one we had one by far. So that these are the ICs. The IR pair, I think we have it. So let's just use the one in the lab. Let me show you how that works. All right, so this one, okay? So how can we make it work? So this is a IR pair. One is a transmitter, one is a receiver. You can see these are the symbols of the two components on each side, and there's a little plastic board in the middle to isolate, so they're not having any crosstalk. So hopefully it's only receiving reflection. Okay, that's the goal of it. And you can see this is a diode, so this must be the transmitter. Okay, it's a light emission diode, LED, IR LED, and the other one is a light sensor. So it has a base, but the base is not a electrical terminal. It receives light and it turns on the channel. So whenever this one emits light and gonna reflect it back to this optical transistor, the CNE is getting shorted, so it having a current flowing through it. So in that case, what I did is I had two resistors connected to these two terminals, and so this one you can see it's in the hundreds level because this is the IR LED, even though it's invisible, but it's still LED. We usually use a current limiting resistor. It could be like from 300 to 600 usually. You can choose like a 320, the typical values, or 560. So we do have these resistors in the lab. So we don't need anything. This is a current limiting resistor. But for the other one, it's trying to put it up to VDD before this channel is on. Okay, you can see if there's no light reflection being received by the optical transistor, there's no current. If there's no current, the terminal here becomes 5 volts. So this must be a pull-up resistor. It's a pull-up resistor. The pull-up resistor, usually we don't even use 1K, 2Ks. We just pick up 10K, okay, for most of the time. It's a pull-up. So the other one is a pull-up, all right? Whenever this guy receives the light, it's shorting CNE. It has a current flowing through CNE from the top. So this terminal will be shorted to ground. So that's how you are getting that varying signal. Because this transistor can be fully or partially turned on, okay, depending on the light intensity. So in that case, the voltage here varies. Does that make sense? Are you guys understanding what I'm saying? And this is not a only digital signal. It's an analog signal because the intensity of the light, of the reflection, is the analog signal, and that's why we want to use it. It's not a comparator. It's just an analog output. So in that case, we are getting an analog signal in the time domain. Okay, so that's the original sensor signal from your fingertip. Because this LED emits light to your fingertip and reflected by the blood vessel, the red blood cells, and reflects to this light sensor. Depending on the light intensity of the reflected light, this one is having a different voltage. Okay, that's how you are seeing a wave. We can still use this one because this sensor really is not magical. We can use whatever we have in the lab, right? We don't have to order a new one. So let's skip that one. Okay, so we can use the one we have. So the thing is, the circuit mechanism will be changed because this is a current sensor, and the one here is a voltage output. VBP. Let's see, what is this? So the LED, no LED, it's a photodiode. The photodiode here being used is a part like this. So what about the emitting though? I'm wondering. Emitting. I'm not seeing an emitter on the circuit. Oh, it's over here. It's at the bottom. These ones, air diode. This guy. So in that case, you have to place this air diode in just next to this guy, which also fine. Okay, let's just use whatever he used over here. And I think let's just put this one over here. This is a quantity 1, right? And what is this? This is a photodiode. And then let's come down here. There's another 1 microohms resistor, so this becomes 2. And there's a 100 picofarad capacitor here, so this becomes 2 as well. Okay. And there's a LT6003. I usually use DigiKey. I mean, let's see if DigiKey has the same thing. DigiKey. This guy. It does have the same stuff. Right, it's a surface mount, but I think we will be able to solder it to 2 wires. That shouldn't be a problem. Can ship immediately, which is great. Put a link here. And then LT6003 from Linear Technologies, the op-amp. And because we are not doing surface mount, so we need a dip. We need a dip version of it. You can see most of them are surface mount. We can still solder it to the prototype PCB. It could be a little bit challenging. Let me see if there's a different footprint. So it's called device package. And it seems like all of them are surface mount. Fine, let's just use it. It's $3, almost $4. Still very expensive. Let me take a look at this one. $4. Yeah, it has to. You have to buy a pretty large volume in order to bring the cost down to 1 point something dollars. But I believe if there's a vendor we can buy from Alibaba or somewhere, it could be like only 20 something cents. Because it's really not a high technology stuff. So it's 1.6 volts power supply. So it's not the regular ones that we use in the lab, like the 5 volts easily, right? So you can tell that it's a 1.6 to 16, all right, 1.6 to 16. And the VDD here is, I couldn't tell actually from VCC, but it seems like it's somewhere around 3.3 volts because it's a 1 volt as an offsite, right? So let's just. So the only concern is this could be very small, then it can be a little bit challenging to solder, but I think I can figure that out. Just get some wires soldered to the pins and plug it into the breadboard. It should work. Okay, let's just do this. I mean, we don't have time to design the PCB, and it's not really related to this class. Okay, but building a PCB is really simple. I can teach you guys how to do that later, but we'll just solder wires to this guy, okay? This is LT6003. How many do we need? 1, 2, right? Because this one is a peak detector. It's not the waveform amplifier anymore. All right. Is that the case? Compare out, because this is the output, and here's the peak detector, and here's the pulse. I think we only need a two. Only need two of them. 1 and 2. Okay, so this one is 2, and here's a link, just post it here, and this is the op-amp, right? We don't have another column for the footprint, but we have the link. Have the link here to show the footprint. And now let's come back. 3.3 micro. It's a pretty big capacitor. I don't think we have it, so we have to order it. 3.3 micro farad. And it's probably gonna be electrolyte, like one of these ones, and pick up the one that has a lot of in stock. It's 50 volts. It's way above that voltage rating. And you can see this one is pretty cheap, and let's see how many do we need over here. 3.3 micro, 1, oh, just one. Okay. Just need a 1. $56K. I don't think we have it. Do we have it? It might be somewhere, but let's just order it. 56K rod. This is really common. Jeez, even this is 1 cent. Oh no, 10 cents for each. That's crazy. Should be dirt cheap. It's just 10 cents. Hmm?
Top right. Did you keep the tariff resource update?
Uh-huh. This one?
Yeah.
Trump? I've been paying tariffs on DigiKey for a few years, since the tariffs getting added. Yeah, I believe even though they're selling this for like 10 cents, but still, it's still imported from China. I mean, all these are from China. I mean, China is probably 100 times cheaper. I mean, I couldn't believe like one resistor is 10 cents US cents. That's crazy. It should be 100 times cheaper than that. I mean, for 10 cents in the US dollar, it should get 100. Should get 100 in China. Let's just put it here. This is 56K. It's a rod. And how many do we need? Just one. Okay. 1K we need a lot. We have a lot here as well, so we don't really need to purchase it. We have 1 mega and 1K. We have a lot. So this is also 1 here. Just by default, it's always rod. I think we don't have other packages since it's just on the breadboard. 1 micro. I think we have a lot, but just in case. 1 microfarads. Definitely not these surface mount since we don't have a PCB. So pick up the raw ones. 1 micro is still considered a big capacitor. And pick up the ones that has a lot in stock. And put a link here. 15 cents.
Quick question.
Uh-huh.
Do you want us to make our own schematic?
Or not. It's not a PCB.
Okay. I just thought But we're still like designing our own on a breadboard. You're just showing how we would do it.
Yeah, yeah.
Okay.
You can design your own PCB and list the parts, no problem. But just showing a typical design over here, and there's no schematic, no PCB. Okay, no PCB. Almost done, right? We're getting to the 1 microfarads and 33K. We don't have it. We need a 1. Rod. Link. 1 mega. It's another 1 mega, so increase the number to 3. And 5.6 nanofarads. It doesn't have the ceramic material, capacitors, it's only the film capacitors in the nano level. Interesting. Let's see if this one has some options over here. It's all surface mount. Interesting. If you pick up the packages, through hole, pick up through hole, apply. Then you got all these options. And this one, available to order, what does that mean? Sometimes it takes a lot of lead time to get things shipped. It's 0 in stock. I mean, you can search for capacitors and come to this one. Oh no. Film. Let's try film this time. And here's the list of all these values. For nanofarads, it's 5600 pico, right? So we can also find out in a pico range. This guy. Apply. Here it is, 5600 picofarads, which is 5.6 nano. And let's select it. And it's 7,000 something stock. And it's 28 cents. Let's just order this guy. It's 5.6 nanofarads. And if it's 1, this is film, which is fine, it's just through hole, right? That's 5.6 nano, and 1 mega have it. This is right in there. 2.7 kilo and 10 nano. That's the only 2 components left. Oh, we still have this one, but let's get into that later. But now, pick up the 2.7K resistor. $3 for each? Nope. So pickup one has a lot in stock, like the 70,000 in stock is still 10 cents. So it's reasonable range. Okay, so this is the 2.7K and just the one. All right. No, it's 12.7K. It's not 2.7K. Come back. Select this one instead. So the link is here instead of this one. All right. Yeah, I think doing this is necessary just in case you have a lot of things in the cart. Either they are not in stock or they are like $30 for a resistor. 10 nano. The capacitor is a little bit interesting. Let's still use search for capacitors first. Then get into this. It's a nano range. Let me see. I just do film. And we're picking up 10 nano. 10 nano will be 10,000 pico. So it doesn't have 10,000 pico here. Then we can also pick up 0.01 micro. Okay, so this is also 100, also 10 nano. So 0.01 microfarads, and we want a through hole because we are doing everything on the breadboard. And let's pick up the one that has a lot in stock. There's 200 something in stock. Let's click. 76 cents. That's crazy. Let's do it. 10 nano. 1. Film. Okay, so I think at this output here, we should be able to get the analog voltage. We don't need to go further because next, this one doesn't have any gain here. It's a voltage follower, no gain, and this is the peak detector. So nothing is getting further amplified after this point, and we don't really need any of these. So now, the only thing left is emitter, IR diode. So it's IR diode. The 68 is the current limiting resistor. We can find it out in the lab easily. Doesn't have to be 68 because it's the current limiting. Doesn't like the resistors and capacitors in the middle because these are filters. These filters are participating in that equation. It's 1 over 2 pi RC. It's defining the cutoff frequency, right? So these are critical. But these ones are not. So the current limiting resistor 68, it can pick up 100, it can pick up 50. It doesn't really matter. It's just the current limiting. Okay. So the IR diode, we can use the IR diode from the pi here, right? We just take it out and just use that IR diode, which is fine. So we don't have to order that one. And there's a transistor, and it's getting a gate here, so I believe it's just adding a switch to it. Because pin number 2, let's see where pin number 2 is connected to. Pin number 2. You can use you can just turn it on. I don't think this is necessary. This transistor, you just keep it on, right? Just keep it on. It should be fine. You plug it into have a VCC and ground, so it's getting current flowing through it. Just turn it on. You're getting a little NMOS here. It's just trying to performing like a switch. You can turn it on and off. Okay, and for this part, it's necessary. And why is that? Because making a it's a voltage divider circuit to creating that 1 volt, creating that 1 volt offset voltage. You can see from VCC it comes down to this 3.3K and then to this resistor. Let's do a calculation because these are all DC. Guys, these are all DC. What is happening here? If you see a symbol like this, what is this device? Zener diode. And you are doing a reverse connection. It's a reverse biased. Why?
It's because Zener diodes work in reverse bias.
Yes. So how that works? It's doing this, right? Oh, I should make it flatter here, but so the Zener diode reversely biased, and there will be a voltage getting stabilized at this point. So this is usually, I believe this is 2 volts. It's 2 volts. Why is it 2 volts? Because you can see here, this is the output of Zener diode, and eventually you have a 2 equivalent resistors, and you are picking up the voltage in the middle. So that means it's 50% in the middle, and which is 1 volt. So in that case, this point has to be 2 volts. So this Zener diode has to be rated at 2 volts. Let's search for that. LM 4040 B20. Okay, so it shows a Zener diode symbol, but actually it's a reference. It's a voltage reference IC. It's this guy. Okay. Data sheet. So it's a resistor and Zener diode inside with IC. This is a schematic of the IC. Fixed output voltage 2.048, 2.5, 3 volts, have all these different options. How do we know which one is the one we used? I know it has to be 2 volts, but how do we know? Is there a way to control it? It's probably depending on the RS, right?
Yeah.
Let's see. Okay, so basically inside is just a Zener diode. Okay, and I'm trying to find out the RS value. How do we calculate it? It shouldn't be determined by RS. It's interesting.
And they probably have a sheet that just shows all the Zener diodes, right? And like what voltages they have right now.
Here, that's the equation. IL plus IZ. RS is calculated according to equation 1. So you have to design RS yourself, which is this guy, okay? And if you plug that in, I think VS we have is I don't know yet. It's something provided. We can look through that website and see what's the VCC being used over here. But the question is, how do we find out the currents, right? You can measure it. Need to take some time to look through this and to find out the parameters to be used. But I think this doesn't affect anything about the part, right? So we can still order the part. And go through this data sheet and study this a little bit and put on the report, okay? Shouldn't be that difficult. You can see fixed output voltages for all these voltages. There must be a way, but there must be a place that shows the calculation for that. Okay, but at least you can see there's an option for 2.048 volts. So we will be able to configure it to output a 2 volts DC, and that 2 volts DC will come back here through the volt divider and give you that 1 volt output as a DC offset for all these op amps. So in that case, you just need a 1 VCC. Keep in mind, even though you are doing this in the lab, you always want to think about the practical way in the real world, right? So you don't want to have like a multiple voltage sources from the benchtop power supply, like have like over 10 cables hooked up to your circuit. That's not really practical. So usually, for all these devices, you only have one power supply, right? Just one battery, and powers up everything. So the same thing here. You only have one VCC, and that VCC generates that DC offset for the op amps through this circuit, through this reference voltage regulator, or the Zener diode. So let's put this one in the boom list. This is a VREF. It's 1. And it requires a 3.3K resistor and 22K resistor and all these caps. 1 micro, 100 nano. I think we had it here. 1 micro just changed to 2. 100 nano, we don't have it yet. So these capacitors are just used for low pass filters. Okay, stabilizing the DC voltage output over here. So any high frequency noises will go through this capacitor and short it to ground. So these are just stabilizing the DC voltage. Keep in mind. So 100 nano, let's just get the value, specific value for the capacitor. So 100 nano, I believe we can pick up a electrolyte cap. It's because it's a little bit big. 100 nano is 0.1 micro actually, right? So apply. And choose the one that has a lot in stock. Doesn't have too many options. Interesting. It's a surprise. So let's go back to the film. Go to the ceramic ones. Or film. Film probably is good for this range. So that is 0.1 micro farad. All right, so that's the right one to choose because this has a lot in here. 100 nano or 0.1 micro. We saw a film and one of them. 22K doesn't really have to be 22K, but I think it's involved in a certain calculation of the equation that we found in the datasheet. So let's just stick to it. So 3.3K and 22K. I don't believe I have any of them over here, so I don't have them. So 3.3K and 22K. 3.3K. It's a 3K ohms. It doesn't have 3.3K. Let's see if I choose a specific value for that capacitor. It doesn't have that option. So 3K is the one available. It should have 3.3K. I don't know why it's not showing. Oh, I put a comma here instead of a dot. 0.3K. Disconnect from the internet. I use my hotspot. Do you guys still have internet?
Yeah, it's getting slow, but I think people are.
In courts help and flip the.
Okay, so I think the two remaining parts are the 22K and 3.3K. You can use a similar way to find it from DigiKey and put in the card, so I can directly check out from your card, right? Let's see. So there are different options from. I think there was a microchip version, also looks pretty good. So you can open it. This one. So here's the IR pair. One emitter, one. Oh, it has two different colors for a reason. That reminds me about the circuit when we are calculating the SPO2. Yeah, because it's a course project, right? So you guys should do some research on that calculation. The get lines on SPO2 measurement.
Yeah, because that's a ratio, right?
Yeah, so you may need a right diode as well. I mean, right LED.
Yeah, because you need to measure the difference, the ratio between the two different wavelengths.
Yes, exactly. So there's a right one and a IR one.
Yeah.
It's calculating the ratio here. R is determined by the following equation. Y calibration required. So in addition to find out the heart rate, if you can calculate the SPO2 through that two light sources, that'll be great. That'll be even better. So you can see this circuit also has a right diode here. So you need two of them. So in that case, wait, you got two light sources, but only one detector? You see this one has the two LEDs next to each other, right? Oh, I got it. It might be controlled. That is why it's using an NMOS here. It's using a microcontroller to control the timing. Right? So turn on this one, measure it. Turn on this one, measure it.
Yeah.
So that's why it's just the one detector.
Yeah, that's not using pulse width modulation to switch between the two. That's at least what I
It just
was
pulses, right? You don't need a PWM. What do you mean by modulation?
I was reading an article,
Uh-huh.
and they were using pulse width modulation to basically control the whole system, basically for timing. It was a clock.
Yeah.
It wasn't. It was basically just a pulse, but that's what the phrasing for it.
Yeah, the PWM is measure the power output, right? But
Yeah.
for enable, if it's just used as an enable pulse,
Yeah, it was weird. I didn't know why they were using it as just an enable
Yeah.
pulse. It was basically just a clock.
yeah.
But I was told that you need to alternate the two different
Yes.
lights. They can't be on at the same time.
That's right. Let's take a look. Do you know how to program with Arduinos? You do, right? Just pin out high, low, right? Just oscillate. It's a really simple pulse. Turning on and off that NMOS transistor. So this one is from microchip. It's a different diagram, but shows the idea about the output. So you can see that the oscilloscope shows both right and IR. And it's comparing the RMS voltage. Have to find out how do you calculate it from the pulse, from the oscilloscope reading. Sample calibration curve. circuit description, LED driver circuit, timing diagram, read ADC, IR on, write on. It doesn't have to follow this timing diagram exactly, right? Just turning on red for a certain period of time. And then turning on the IR. So reading the ADC only takes a little bit of time over here in the middle. LED current intensity is controlled by a 12-bit DAC. It's complicating things. So there will be 2 ADC channels. How do we do that? So the ADC of the IPGAs, it does have a lot of channels, right? If you're adding a new task to it to let you multiplex channels, I'm afraid that we won't be able to finish it by the time. It seems like we do need 2 different channels. That's a little bit too much, I think, for the rest of 3 to 4 weeks. A little bit too much.
So we don't have to do the multiplexing for the ADC?
Yeah, I think it's a little bit too much. So let's take a look at this schematic really quick and see what's done here, what's being done here. So basically not too much difference over here, right? See? It's a diode cathode anode, so it's basically a current photodiode connected to the two terminals. And the same thing, it's a low pass filter here, and then the high pass filter here, and then another low pass filter plus amplifier. That's it. So by comparing these 2 schematics, I think this is the one we want to use. Okay, same structure, but a little bit different values. But eventually, I believe the corner frequency will be very similar. I can see the second stage for the DC part is amplifying by 22 times. Adding this low pass filter to it. That's a low pass filter. That's a DC amplification. It's 22. 220K divided by 10K is 22 times amplification. And the first stage is the current to voltage converter, it's a TIA, plus the low pass filter. So same structure, okay? Just 2 stages. One stage is a current to voltage converter. The second stage is the voltage amplifier. Okay? So in your report, keep in mind, in your report, you have to show the corner frequency of all these filters. Do a calculation. Should be really simple, right? You have learned it in circuit 1.
Yeah. Well, I was gonna ask, why are the cutoff frequencies, like, for the low pass filters and the amplifiers so high? Because I have the formula right here, and they're like,
Yeah, let's calculate it. See what's that.
yeah, they're really high. Like, really
2 pi. So it's 6.2 pi RC, right?
Yeah.
2 pi times 1,000.
Well, it's 100K.
And then times 2 to the -9, right? So it's going to be 1 over. So this number times 10 to the 9th. So it's basically this. Hertz.
Yeah, it's really high. 'Cause-
Yeah, it's trying to get rid of the high frequency noises from something, you know, it's
Okay.
from the machine, I guess. Let me see what the other one is at. Did you calculate this one? It's the same? 1 mega?
Yeah, it's about the same.
So 1 mega times. This is smaller. This is smaller.
Yeah, that one's a lot smaller. That one's like
Yeah.
16 hertz for cutoff frequency. This Pico's 10 to the negative 12. Right?
Yeah, this is like 1.6 K, I think. 1.6 K hertz. I think either one works, just depending on how what's the frequency you want to look at. It's probably not affecting anything because your signal's frequency is so low,
Yeah.
right? I don't think that matters too much. If you look at mine, I think I used I didn't even do it. I had a 1 here, trying to remove the 60 hertz low pass. So anything lower than I think 100 hertz or something will pass because. Did you calculate this one? How much is this low pass here?
Yeah, I think that one's 4.8, which makes sense because the range typically I found while reading papers was between 0.5 and 8 hertz, but 8 was kind of stretching it. Most people were saying 5 or 6 was better. So yeah, these ones seem right. I was just curious about the filters on the amplifiers. It looks like they're mostly just for gain values and like filtering super high frequency, except for that one, which is about 16 hertz.
Yeah. Yeah, it's trying to use a pretty high resistor to increase the gain, right?
Yeah.
Yeah, I don't think the low pass filter does anything here. Oh, because it's trying to increase the gain, so it has to pick up a high resistor, and you really don't have anything higher than 1 mega ohms available, right? So it picks up the highest resistor, and then it's trying to offset that, so it has to pick up a low capacitor.
Okay. Yeah, it's trying to
Wait,
It's
but doesn't have to, right? Why it has to pick up a low capacitor though?
I thought there
to
was a
power
downside
C
to
to-
having high gain. Because there's a downside to making a really high resistor, isn't there?
It's a current signal, so it's okay.
Okay.
So the gain here is actually 1 mega.
Yeah.
It's a TIA. It's a current to voltage converter. It's not a voltage amplifier.
Yeah.
If it's a voltage amplifier, you don't want to amplify it for too much because, for example, this stage, right? 1 mega over this one is only like 30 times gain. As you can see from the microchip, It's only 22. It's only 22. So it seems like the 20 to 30 is a right range for the op amp, but usually I use the lower ones. It's 20 something is still a little bit concerning me, a bit too high for me, but it's able to filter things out because
In your circuit, you did like 50 times.
no, did I?
Yeah.
I did it for each one. Oh, because this is a high precision amplifier. It's not a regular amplifier.
Okay.
It's an instrumentation amplifier. Has really low DC changes. It's being amplified. So eventually, I'm having like 2,000 something times of amplification, and then the signal is still tiny. But keep in mind, this is the voltage signal. It's different, right? It's a voltage signal. It's in millivolts from a fingertip. So it's a voltage signal being amplified by 50 times 50, which is 2,500 times of the voltage amplification. However, for this one, it's different. It only has, you can see the previous one has 22 times, has 30 something times, and this one has 22 times. But keep in mind, it's a current to voltage amplifier first, and then you got a voltage here already from the current, and then you amplify the then you amplify the voltage for 22 times. So you can imagine that this voltage here must be a lot higher than the voltage directly from your fingertip, because it's not it's not a voltage signal, it's a current signal. Okay, it's a current signal from the photodiode, and the current is already amplified by, you can see here is 100K times, and for the previous example is like a 1 mega times. Okay, so it's different strategies. Okay, different strategies. I think either one works. And this one directly has a video demonstration, so I trust it. And so the only thing here is, do we still need to calculate that SpO2? I think if we're doing an Arduino project, we can easily get it done within like 2 weeks. But ADC is on the IPGA. We have to figure that out first and use different channels to handle the timing. So let's do this. The first task, I'll add bonus points if you guys can really calculate that SpO2 parameter in your report, okay? But otherwise, as long as you guys can show that wave in your serial monitor, you get full points for the project. So the goal is just to show the wave, okay? So to show the wave, and then you can use oscilloscope. No, actually, it's your not oscilloscope, the serial monitor of the Arduino IDE, right? Plotting the waves. If you can plot the wave in Arduino IDE, you will be able to export it, but we don't need to export it. But you just plot the waveform in IDE, then we'll call it a success, all right, for this time. Maybe next semester when I teach this again, I will ask these people to use whatever you guys already built and start from there to calculate the SpO2 parameters, having some meaningful biomedical information from it. Okay? Okay, so we are just looking at the waveform and calculate the heart rate. That's it. Okay, one more thing about the ports that I didn't cover too much in the past. Any question on the project, on the preamplification at least?
So for the, I guess like what you want us to do, you don't want us to make our own schematic, like just use
You can make yours, definitely. You can make yours. I was just showing the how to make it, because I was expecting like if I don't do this, eventually there will be a lot of things to fix in your cart. Probably it's going to take a lot of time. So showing you this one to let you know the packages, you know, the cost and all these kind of things. I will start putting things in my cart if I see that, oh, you already ordered something, I already have 100 order in the cart. So keep in mind, for all the like 10 cents, resistors and capacitors, I'm not just going to order one of them. I'm going to order like hundreds of them. If I'm looking at your card, why? Usually the packages are coming with like 500 or 1,000 in there. So I was looking at your car. If I'm looking at your car, I see the parts already in my card. I'll just delete it. Make sense? So I don't have to order like just one single resistor from your card. I'll just delete, and just leave the ones that I don't have in my card. Okay, make sense? Right. And for other parts of the project, definitely, because it's a course project, I hope you guys have your own design if you can. And these are all the examples. And so these figures is snapshots when I followed that XADC tutorial from Xilinx website, and it worked. So there's an official tutorial and GitHub. You just directly use that bitstream file and make correct connections, and you should be able to see ADC signals at your 7-second display. It's a really good example. And that's just the ADC part of it, okay? If you are connecting the ADC to the SPI module, and I have 2 examples here for you guys to follow. You can see from last semester, people already built it. So the ADCs is connecting to the switch, the potentiometer, okay, and the SPI. So it digitizes the analog signal and directly connect to the SPI module inside the IPGA, and IPGA export that SPI signal in the serial form. So the serial signal will be sent to the Arduino through this level shifter, because this is a 3.3 volts device, this is a 5 volts device. So you need a level shifter. Any digital signal oscillating from 0 to 5 will be converted to 0 to 3.3 volts logic to the other side. You can see this is just very simple level shifter. You just connect the wires to it. So this is as a just level shifter in the middle, converts voltage from 3.3 to 5 to 3.3. So your basic 3 board is safe. You can see Taylor was able to read all these analog values in the serial monitor instead of plotting. So you guys are going to plot it instead of just showing the numbers. So the code and everything is already provided on the website. This is one example, and there's another example from Ian, and you can directly use. So this was a project diagram from last year. You can see the analog signal comes from the potentiometer. We didn't actually amplify anything, so we just directly use the potentiometer's voltage. Just potentiometer, we replaced everything here. Just use the potentiometer and give an analog input, digitize it. So the basic 3 board has the SPI, has all these leader follower modules, and communicating with the commercial SPI module in the Arduino through this level shifter, and then plug everything to the serial monitor in your laptop or desktop. And the code is provided so you can directly use it. I remember it was not super perfect for some reason, but I cannot remember. But at least you can see the analog signal was able to be received by the Arduino and displayed over there. Okay, that shouldn't be a problem. So when you guys are forming teams, make sure that you have one person working on that preamplification and one person working on the XADC and SPI, and you don't have to wait until you receive the parts to start working on the XADC, because it's already provided. All the examples and everything can get started right away. And I think the person who works on the preamplification can start working on the list of the parts and put in the cart of DigiKey. At the same time, maybe drafting the report, doing something else, and another person can start working on the x86 and SPI as soon as possible. So you can split the tasks evenly, and eventually you can test both modules on separately. For example, the x86 can use a potentiometer to make some fake analog signals, right? To let it digitize the potentiometer's analog output and trying to plot it. When you are twisting that little potentiometer, you should see an analog wave, right? So you can plot it in your serial monitor on Arduino. So this is a separate task from the amplification. So the other one work on the amplification can use I just plot it through the oscilloscope. Okay, just plot it on the oscilloscope. So don't need a digitizer. Right, because the oscilloscope has an ADC in it, has a display module on it. You know, it's really nice. But the thing is, it's $3,000. Right? Okay. So you understand that why we are not using oscilloscope. Right, it's just for probing. It's not for a product, right? Okay, and one more thing before I let you guys work on your own stuff. So I will stay in my office for most of the day today and to get the things ordered. Oh, I think we still have time for the lab, right? So we can order things before the end of the lab. Hopefully we can get things ordered, okay? Okay, one more thing about the soft core stuff. A lot of assignments, right? Soft core lab has a week 2 lab report due sometime, and you got a UART, you got a SPI.
Like a write-up?
No, just lab, right? Yeah. Snapshots. Okay, input output. It could be a little bit confusing here. I added several snapshots to the tutorial, trying to clarify everything. I think I have another tutorial here. So let me ask you a question here. For the Picoblaze core, all right, does it have other peripherals or just the core? Does it have the ports, multiplexers? Let me show you one picture here. See this one? This is from the official guide, all right? General purpose IOs. Does the core have these things? The decoders for the port ID.
Yes. Oh, it's not like literally, but
It doesn't. It doesn't even have this guy. So the KCP SM6, when you instantiate it in your top, it doesn't have any of these. No, it's just a core. Just a piece of core. And has all the ports available. So you can connect to the ports. Okay? So if you do your assembly code, you program your assembly code, and use assembler to convert it to a .v file, and it creates a little .v file, right? And then you instantiate that .v file like a memory, as instruction memory, in your top. Remember we did that? It's like a prog ROM something, right? So that is this guy. You add it to it. It doesn't have instruction memory with it. You did it. Same to the ports. It doesn't have all these multiplexers and decoders. It doesn't. So when you are doing input and output, you have to program the ports yourself, the decoders and multiplexers yourself. How do you do that? Again, the template shows you the examples. What's the template? The template is from the folder you downloaded from my wife's site. Right? Has all the examples. If you scroll down, you'll see there are input-output decoder examples. Okay? So remember when you are programming your top module for your soft core example, right? So you have your program instruction memory over here. And you have your core instantiated. And also at the bottom, you have some like always add something, do something, right? So all these are the space or the opportunities that you can program the logic for these things. Look at this example. Look at this example. How many bits do you have for the port ID? In theory or physically? Look at this one.
That's 255.
256, right? From 0 to 255.
Yeah.
So you have 8 bits you can modify for the port ID. However, do you have to use all of them? No. Why? Because you don't have many things that you want to use that many different ports. So what you do is, for this example, you only need four different ports. So how do you program a little multiplexer and decoder circuit like this? Keep in mind you are doing design automation in Verilog, right? If you program in Verilog like this, it's just a case statement. That's the decoder, right? Case statement. Decoder is you see this, you output this, right? That's a decoder. Same thing for case. In Verilog, you realize you implement that decoder using a case statement. It's a decoder. If you see a port ID from it's 2 bits, right? 2 bits. 0001 1011 doesn't matter. So if you have port ID of 00, you send this input to the import. Keep in mind, import is always the physical import. I was pointing here, but actually I'm looking at the code for the import. But similar, okay? There's a multiplexer here. So the import is an 8-bit pin. It has 8 metal wires. And you can use this port ID to control this multiplexer to send which one you want to use and which one you want to send it to the import over here. So 4 options. That's a multiplexer you can program. So this little case statement over here, eventually you synthesize it, it's going to generate a multiplexer like this in your FPGA, and that interface with your core. Same to the output. Same thing, okay? Output. Depending on the port ID, you send the output. So output is the keyword of the core, right? So that's the output of the core. It's 8 bits. You are sending this one to output WXYZ. You have 4 different options. So these ones, WXYZ. So you are sending this 8-bit signal to here, 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 or here. And if you are looking at the declaration of all these wires and things in your top module, look at the Verilog top. So at the very beginning, you declare port ID, you declare output, you declare import. So keep in mind, these are just the wires and register type variables or vectors. Why do you need to declare these ones? Why? In your top. Why do you need to declare these ones? Because in your top Verilog, you are going to instantiate your core. Okay? If you instantiate the core has output, import, and port ID. And also you are trying to generate a Verilog circuit like this. So these wires and registers are performing like an intermediate connection, like media in the middle. So you can connect your core to that register or wire, and you can connect your peripherals to that register wire. So you can make indirect connections from your peripherals to the core. It's like remember when we are doing the flighter experiment or lab, we declare wires, right? So we have a little floating wire in the middle, so when we do the instantiation, you make the connection here and here, right? On the two sides. Eventually they are interconnected. That's why we declare these ones on the top. But for the example we did for the tutorial, these were really simple. We didn't have any multiplexer. Remember the code like this? Right? We don't even need the multiplexers. It's just one port. And you can see through the declaration here, from the instantiation, right? So that's the core, right? We instantiate the core. And you see the core's import is shorted to where? To the switch. So what's happening is we don't even have this multiplexer. So the import here is directly shorted to the switch. So whenever you change anything to the switch, the signal will be directly sent to the import. You can see here as well for the output, right? Remember for this example, what we did is we changed the values on the switch and directly shows that value on the LEDs, right? So for the output of the core is shorted to the output wire. Remember we declared the wires in the output here in the top. So output is the wire, and we short this to the output. And in the Verilog, eventually we directly connect that wire to the LED. So that is why the output doesn't need a multiplexer or decoder as well. It's physically connected to the LEDs. That's why we saw the results, and we didn't need to do anything to the decoder. And when we are programming the assembly, we just directly use 0, 0. It doesn't really matter. I mean, because we don't have any logic in the middle. It's a port ID. It just have to, syntax-wise, you have to put a port ID in there. But the port ID is not doing anything, is it? You just think about how you declare the port ID. The port ID is not doing anything. Because the import is physically shorted to the switch, and output is physically shorted to the LED. Who cares? I mean, who cares the port ID? There's no multiplexer, no decoder. Nobody cares. You do the switch, it directly shows up at the import. And the core will process this input signal and directly send it to the output. And the output is physically shorted to the LED, so this shows up on the LED. All right. That's everything I'm going to cover, and we'll see you in the lab today, and so we'll finish all the ordering of the parts. Okay? See you later today.
Yeah, see you later.